because I mean we're supposed to be curious. We're cool with the end. We're cool with the sample, the sampling distribution. We're cool with p-hat. What we were a little frustrated with is why were we then taking all this and turning it into z-scores? Like, what was the point with the z-scores? Why z-scores? And then we were discussing how the first step should actually be, before we even start listing off anything or trying to solve, the first thing we should do is this 10% thing, or they call it the law of large numbers, or however you want to remember it. We've got to see if n times p or n times 1 minus p, if that's bigger than or equal to 10. I would check that first, because if that's not true, our population's not normal, and if our sample's not normal. And if we're not normal, then why are we trying to apply this to a normal curve? So we've got to check these conditions, checking for normality. If we don't have this, we're not normal, we can't do any of the stat stuff we want to do. Okay, but our question was, why do we have to go to z-scores? What was the point? And then once we went to a z-score, once we got that percentage, what did that mean? How is that useful? So I was with you. Friday was a long day. So
Where is this on?
it is on your notes. It's page 4 of your old notes. Okay, so page 4 of your old notes is where we're starting. And we're going to go work examples on the other page. But the reason we're doing the z-score part, okay, is back to, Brittany, go away. Jackson, will you shut the door for any other wanderers wandering by?
That was a terrible idea.
Always everybody, and don't lock the door. She threw me off my game. Okay, so we were talking about p-hat, and that hopefully p-hat's our sample proportion, and hopefully p-hat is telling us the truth about our population. When we make a sampling distribution, we talked about cussing, and I don't know how that's happening. Okay, so anyway, we talked about we want p-hat to be normal, hence why we're checking these conditions. If it is normal, then we can use a normal distribution to calculate the probability of attaining a simple random sample in which p-hat lies in a specified interval of values. All that fancy talk is saying is that if our p-hat is actually normal, and we're over here doing our sample distributions with our sample proportions, we can actually start saying smart stuff involving percentages. So I know you're like Miss Compton, you're trying to be a chapter ahead, and I am. And I should have looked over my textbook notes before I tried to say words to you on Friday, and obviously again today, because it's not coming out as properly as I'd like to do. So, everything we've done is building. Back in chapter 1, we started cussing. In chapter 2, we started doing these normal scores. And here we are in chapter 7, and I'm suggesting we're supposed to cuss, do normal scores, and somehow this percentage is telling us something about the population or about the sample proportion that we have. And it's really all leading to the next chapter, where we get to something called a confidence interval. And what happens with a confidence interval is we start saying smart stuff like, that's almost 90% right, you're on my nerves. It says, like 90% of all our simple random samples will give a sample proportion within 2 percentage points of the truth. So we want like a percentage to reference that we're confident with. Like we are confident that 90% of what we wanted actually falls in between that 0.33 and the 0.37. If we took some simple random samples, 90% of the time, it would fall between 0.33 and 0.37. Let me say that one last time because it finally actually sounded like a math thought. We're wanting to put a percentage on it so we can say how confident we are. So we might say 90% of any simple random sample we take, 90% of the time it's going to fall into that range we were looking for. So on Friday we were working through a problem, and I got caught up in the Hobbit land. And we checked to make sure, and I had a blonde moment, and we had this whole discussion about should we do NP or NP hat. It's always NP. If you know the population, which we did, it was 8%. That's the number you should use, not the 12.5. The formula says NP and N times 1 minus P. We got to take that for real. Okay, so anyway, we did a problem where we checked the conditions. We calculated the standard deviation. And then we took that and went to a z-score. And then I always like to, you don't have to, I know Hunter likes to just put it in his calculator. I always like to draw myself a picture of a normal curve, 0 being my mean, 2.34 is what we found is how many standard deviations we are from that mean. And so when we left, I was looking in my formulas page. I'm the Russell Samantha's or somebody's. And so we went to 2.34 under the curve. There you are. Okay, so we went to 2.34 under the curve, but 2.34 was 0.9901. But again, when we're looking at the normal curve, that 0.9901 from here is for the shading to the left. So we really have to do, or 9904, can I not read today? I can't read today, it's 0.34, it's this one. So we had read 2.34, so it should have been 0.9904. Anyway, so that was the area to the white part of the area, and we were wanting the other end of the curve. So I'm going to do 1 minus that, and we get such a tiny percentage, it's less than 1%. So let's read through the problem again, and then we'll try to make that 1% sound useful. So it asked about some hobbits, and it tried to be way too cute. It said that we selected 200 hobbits from a remote community. We found 12.5% willing to time travel. And then could that specific sample, could it really be called traditional? Traditional, the proportion is always 8%. So we were kind of anticipating a no. We got such a small percentage. We're at 0%. So we're not confident at all that this is the traditional hobbit community because of how far away it fell from the mean. So again, really we're calculating this last little bit using the z-curve so we can say how confident we are with our sample. Our sample did a good job. Our sample did not do a good job. We're wanting to put a percentage on it. That way when we start to predict stuff, we're like, I think this would work, but only 75% of the time. Or I think this is a good sample, but only 63% of the time. We're wanting to put a number on it because we are stat students and we always want to put a number on something. Okay, I don't know if I feel like that helps. I feel better about it. Hopefully you feel better too. Sadly, regardless, we've got to work more problems like this. It's so close to 0, you're like, I'm 0% confident. I'm not confident at all. I'm less than 1% confident. I'm less than 1% confident that this hairy-footed community could really be called traditional. So, in fact, I like that. She makes good suggestions when I write words. I'm less than 1% confident. We're going to start calling it confident intervals soon anyway, so might as well go ahead and throw in that confident word. I'm less than 1% confident that this, and I'm just going to throw their own words back at them, that this hairy-footed community really could be called traditional. Okay, but again, so you're like less than 1% confident. Well, I kind of would have guessed that to be, I knew we weren't very confident to begin with because 12.5% is such a higher percentage than 8%. So I was not surprised when we applied this z-curve to our data. I was not surprised that we were that far away from the mean, because 8% to 12.5%, that is a really big jump in life. Okay, I think that helps. So let's look at the next part. It says if Gandalf only selected 100 hobbits, so we've changed our sample size, and found 12.5 only to time travel, would the result be more or less surprising? Explain why. Okay, so if we went back and we changed our n from 200 to 100, what should happen? If we did the exact same stuff we did last week, so we changed our n. Instead of n being 200, we're not going to do n as 100. What would that change? And would our standard deviation increase or decrease? Okay, so if we changed our n, literally I'm just changing everywhere I had a 200, now I have a 100. It's going to completely change our standard deviation. Our standard deviation is now, instead of being 0.0192, I think it's going to be 0.0271. So that means our standard deviation has increased or decreased. Okay, why is Louise the only one who can do math today?
I have a question.
I have an answer.
If the number grew smaller, why did the standard deviation increase?
As our sample size decreases, or as our sample size increases, our standard deviation decreases. The larger the sample, the less variability. That kind of makes cognitive sense. Like, I took a big enough sample, it's going to have less variability going on. So our probability increased because our sample size decreased. Because our standard deviation is bigger. Okay, so we computed our standard deviation. We still got to convert to a z-score, because again, I would like to put some sort of percentage on life, as in I'm this confident, I'm this happy, or whatever. So 100 hobbits would be more or less surprising. So for my z-score, I'm going to do 0.125 minus 0.08, just like last week. But instead of having our old standard deviation in the bottom, I've got to put our new standard deviation in the bottom of 0.0271. So literally just changing the standard deviation is going to change our z, which is going to change our z-score, which is going to change our percentage. So seriously, just changing the sample size changes things. I need to know what z you get when you do that. It's 1.66. This is why table 1 is going to need a prize or something. My God, they're on it like wine on rice. Okay, so I, being me, skipped one step that was important. How do I even know I can apply a z-score? Did I check that this crap was normal?
It's not.
I did not. So I need to do n times p and n times 1 minus p and make sure it's greater than or equal to 10. Hunter says it's not. Let's see. Okay, so our sample size is 100. But our p from the very, very beginning of the whole world, not p hat, our p from the whole population was 8%, so 0.08. So this would be 0.92. And 100 times that's going to be 8, isn't it? And that's not bigger than or equal to 10. So we couldn't have even done that. So again, again, as we were talking the other day, so in real life, that's exactly what I would say. But since we're fake pretending that this is a free response, you and I both know you need to put some words like, these conditions weren't met, but if we pretended, here's what I would do. And that's what I would put, we can't assume normality. But if we could, and then that's where I go to that Z-score and try to apply some usefulness. But no, I agree. Normally in life, if this was a real statistician's problem, they would say, nope, this is not something we would need to even go with further because we're not meeting the conditions. Okay, so we got a Z of 1.66. So I went and looked at my table, which I laid right here. Okay, so 1.66, 1.66, I got 0.9515. So I'm going to do 1 minus that because, again, I'm wanting the area to the right, not the area to the left. So I'm going to do 1 minus 0.9515. And if I did that, I get 0.05? Point something, 0.485. And so I'm going to say that's almost 5%, right? So I'm a little more confident. So 5% confident that this is a traditional community. Again, I'm going to remember how he, I think it was Jackson was like, this is way too trying to be cute with the Hobbit stuff. They're never going to do one this cutesy. I swear it would be much more straightforward as to what to either reference the traditional community part or the time travel part. This problem's way too cutesy. I don't know why I like it so much. Looking back now, I don't. Okay, but Hunter doesn't like to use the Z-table. He likes to put it in his calculator, but apparently he got stuck the other day. So
I can't do it with those because it doesn't give me a mean to work with.
Mean is one, but normalize it.
mean is 1 because we normalized it, and he is correct.
Or 0.
Oh, 0. Sorry. And the standard deviation is an understood 1.
Here's his weights, right?
Panel weights, yeah.
You email Miss Weights.
Uh-huh.
Thank you.
Hey, she never showed me 5 exercises, and neither did you. And you want to show me tomorrow?
Yeah.
Okay. Example 1 is what I want to go back to.
Is it after the normalized with the 1.66 be a lower or a upper?
Okay, so what I would have done is drawn my curve, which I didn't do for once in my life. 0 is here, 1.66 is here. We're wanting above that, so I would say that's the lower 1.66, and then a whole bunch of zeros after that.
Close enough, yeah. 0.0485.
So that's what we got, and 0.0485, and then we ran it up to 5%. Okay, but Hunter doesn't even like to change things to Z-scores. Do we have to convert to Z-scores in order to put it in our calculator and make all this go? Do we recall, or does Hunter recall?
No, you don't.
You don't. So let's go to number 1, part A, and we're not even going to make life this complicated this time. We could go to a Z-score, and of course, you know, in my paper I did, but you don't absolutely have to. Number 2. because it was shorter and I wanted to do the shorter one on Friday, but now we're being brave and we're going to go to the longer one. Okay. So, trains carrying bauxite ore from a mine in Canada to an aluminum processing plant in northern New York State in hopper cars. Filling equipment is used to load on ore onto the hopper cars. When functioning properly, the actual weights of ore loaded into each car by the filling equipment at the mine are approximately normally distributed with a mean of 70 tons and a standard deviation of 0.9 tons. If the mean is greater than 70, the loading mechanism is overfilling. Okay, this actually was very boring to read through, but saying all that, I've seen one very similar to this multiple times. For some reason, they lack the train and even the ore. I've seen an ore problem a couple times. Another reason this one's good is because it sounds like something that could happen in real life. We clearly don't want train cars to be overfilled by some loading mechanism. So, even though it looks boring, it ends up being actually useful. Okay, part A, if the filling equipment is functioning properly, what is the probability that the weight of the ore in a randomly selected car will be 70.7 tons or more? Show your work. Okay. Okay, so you're going to try to make this one complicated, and this is already starting off with something easy. We don't have to apply any of our new stuff about sample distributions. We don't have to do anything that we've not already done before. First thing first, I want to figure out our N. What is our sample size on part A? I just wondered that. What is our sample size?
The filling equipment.
It tells you in the problem. So, what would be a sample in this problem? What's the population? Maybe we do need to list some things. What is the population in this problem?
Is it the ore or the machine?
I would say neither. I would say it's the train cars. And maybe we should be more specific, carrying. They can carry lots of different things. Carrying bauxite ore. And I could keep on going from a mine in Canada, blah, 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 blah. So our specific sample has to deal with the train cars. So back to part A, what's our sample size? If our population is the train cars,
7.7.
smart people. You know when smart people are so like, if our whole population is train cars and we just want to pick a sample, what are we picking from? If our whole population was M&Ms and I'm going to select a sample, what would I select from? The M&Ms. So if our whole population is train cars and we're picking a sample, is it not a specific train car or specific train car? Okay, and in our problem it says they selected a randomly selected car, so what's our sample size? Okay, so we may not even need that, but it's useful to know, because my God, if we don't know the population in the sample, then what are we doing? I don't know, you know what I mean? Okay, yeah, that is exactly what we're doing. Okay, so it tells us specifically that, yes, it says in the problem that we're supposed to assume it's functioning properly. So if we're assuming approximately normal, because it says that specifically in the problem, which means we don't have to test it, because they told us it's cool. We could change to a z-score, which I think is nice and fun in life, but we don't necessarily have to. So it tells us in the problem, what is the mean?
70.
And what are we curious about?
Let's probably be more than that.
Of it being more than that. Now, you and I both, because well, at least me and Mackenzie, we're on that empirical rule, so I would have probably tried to do 70 plus 0.9 is 70.9 and subtracted by that to see if it fit within one standard deviation, because if I have an empirical rule that I would have, but I can't because that's not going to work. So instead, I can change this to z-scores and do 70.7 minus 70 all over my standard deviation, which was 0.9. And I can do that and change it to z-scores if I want to. It's not a problem. I get 0.78, and then I go and I look at my table and I figure all this out, and life is good. But I don't have to do that. I mean, I like that. Don't get me wrong. I'm over here at 0.78. And I get 0.7823, so 1 minus 0.7823. And my answer is 0.2177. I don't mind doing that. That's not a problem for me. So I'm going to say something about 21%. Woo. However, I don't have to do this. Instead, I could on my calculator. What button do I press?
Second bars.
Okay, and then what's the command?
Normal CDF.
Okay, so all you would actually have to show on your paper is normal CDF, and then you have to tell them what you did for the bounds. So for the lower,
70.7.
the upper,
1,000.
the mean, and the standard deviation. So again, you could normalize it and put in your mean as 1, your mean is 0, your standard deviation is 1, and your lower as the 0.78, and the upper is going on forever. So we're asking, back through the question I can read today, I swear. It says, what is the probability that the weight of the ore in a randomly selected car will be more than this? So we're wanting to know this end of the tail. So that's why Hunter is saying for the lower, put 70.7. For the upper, put 1 with a bunch of zeros. For the mean, we were told in the problem the mean 70. For the standard deviation, put 0.9. And you're automatically going to get the same answer of 0.2177.
But how is this different from when we initially did this?
It's not. Literally, we knew all this in chapter 2. So back to darn problems and stats, you're not necessarily going to have to use the new stuff yet. That's waiting for part B and C and D. Okay, all it said was, what is the probability, which we calculated, and then show your work. Did we do that? Yes. Normally I would say put your words, but I don't need to because of part B. Part B says, suppose that the weight of ore in a randomly selected car is 70.7. Would that fact make you suspect that the loading mechanism is overfilling the cars? Justify your answer. Okay, so he says no because why?
It's less than a standard deviation away from the mean.
That's true.
Out of the entire train.
So a smart person would say something about, I didn't pick a large enough sample to be saying anything to begin with. Another smart person would reference the fact that it's so close to being within standard deviations of the mean. Both those are completely acceptable answers. I'm just trying to make it about what we were previously discussing. So I'm going to say no because I could have done that. I was going to seriously say, I'm going to reference this number. We expect 22% of the train cars, or we are confident that 22%, we expect something about the 22% here. We expect 22% of the train cars to weigh 70.7 tons or more. I liked Hunter's answer. I like Mackenzie's answer. Literally, I'm only putting it phrased this way just because of the ones we've been working lately. Are their reasonings just as valid? 100%.
Wait, doesn't that mean though it's overfilling though? Because anything over 70 is overfilling.
Yes. So it's overfilled.
Yeah, but it says
Yes.
So would you not say that it is overfilled? Because, it's 20%, that's still overflowing train cars.
It's only
I was
one
gonna say
car.
because it was only
Yeah,
22.
sure, but that's
I
still
was.
one out of
I
five
thought
cars.
22% was so small.
That's still 1 out of 5 cars being overfilled just by the probability anyway.
Again, and this is why Louise is like, dang, I wish I was back in calculus. Calculus is so black and white. If you're going to argue that, you can. You could say yes, because what he's saying about 1 out of 5 train cars are being overfilled. Both depends on what words. Depends on what words you put. And I'm still cool with I shouldn't make any I should not allude to anything because our sample was too small. We only checked 1 car. I'm cool with that. Or I was cool with his argument about the standard deviation being, there being such a small difference that it didn't really matter. I'm cool with any of them. As long as you use your words, it's going to be fine. Okay, so you used your words whichever way you liked. If you're with me and that 22 is small, I bet the train people would love me. Or if you're with Louise and you think 22 is pretty big of a deal, so we have a problem. Regardless, we finally get to life where we have a bigger sample. So it says, if the filling equipment is functioning properly, what is the probability that a random sample of 10 cars will have a mean or of 70.7 tons or more? Show your work. Should we? What was the n times p and the n times 1 minus p? What was that helping us justify? If it was normal. And we were told at the beginning of this thing, assume normal. So otherwise, heck yeah, every single time. But thankfully we were told that, so one less step we have to do in life. So, which I could, end of sample of 10 is greater than 70. Since our n is bigger now, I think it would be best to do the formula we've been discussing. I want to know it did.
And now since we have a sample, it's going to be here.
Yes. So I'm cool if you're mad at that. I think I just put SD on my paper. So if you're mad at that specific notation because you're like, I'm not actually going to calculate all that, that's true. Okay, so in our first problem, which is why I was making a big deal about the sample size, in A and B we were talking about 1. 1, we're not going to change anything with our standard deviation. But if you recall in life, you're supposed to take your standard deviation and divide by the square root of your sample size with sample means. Now, you and I have been dealing with sample proportions, and you and I are trying to do this, and we only have to do that because we're already told this time. Again, it's back to, was I given the population standard deviation, or was I given the sample standard deviation? Whose standard deviation was I given? Since we're given the whole population standard deviation, we just have to do, our standard deviation was 0.9, and we have to divide by the square root of our sample size, which is 10. But it's just, again, stupid. Stats would be great if you didn't have to pay so much attention to, okay, the standard deviation they gave me, was it dealing with the population? Or the standard deviation they gave me, was it dealing with just my sample? So since it's the population, we're not using the one we've been using. Okay, you type this in your calculator, you should get something. This, you got 0.5.
No, just the whole thing. After that, I got 0.285.
Yeah, that's what I got. So 285, and you and I are on the same page. So that's cool. Okay, and then if Jackson was live, he would make some sort of comment. So since our sample size has increased, Are we surprised that our standard deviation decreased?
Not anymore.
No. Well, this is kind of boring. One of these stats is only going to get worse from here.
No, boring. Warm, not boring.
It's only going to get worse from here. What are you going to do? Yeah.
Why wouldn't you use why wouldn't you find the standard deviation for the example? Because the sample's different. That's the population standard deviation.
I was going to then change it to a z-score and then do all the things.
Wait, I thought we just found the
Wouldn't you have to find the sample standard deviation and then the sample mean?
Say your words again.
Because you're using a sample, so wouldn't you have to find the sample standard deviation first and then the sample mean? I swear, I turn it off. My light pocket turns it on or something.
Your pocket turned on
I
your
swear it
phone.
does. It's like this little switch. So
Turned on my
like,
pocket.
Your pocket turned on.
I will wear pants. I will not have it last night. Excuse me.
The sample standard deviation
Gross.
and the sample mean. Why?
From 13.
Why?
Which part? The scrub part or the standard deviation?
The standard deviation.
Well,
I'll
because-
find it.
because it's a sample, so we have to find the sample standard deviation first and then divide by the number of square root of the number of the sample.
Are we just, but how would we do that for this?
Yeah, but it's a sample standard deviation. You can say whether or not it's population or not. So let's-
No,
let's assume.
he's back on this.
Yeah.
Of why am I doing the top formula and not the bottom one?
I mean, you can solve for it. You just have the number and you just found the proportion. It's like 22%, something like that. So you can solve for it.
Yeah, but that was for a different sample size. That was for a sample size of 1 instead of a sample size of 10.
Oh, I mean, like, that doesn't make sense why you would use the population standard deviation for that.
Well, if we're being honest, anytime I'm giving information about the population as a whole, I'm going to use that crap. That's the more important. Population trumps sample. We're only having to do the bottom when we don't know population. Because we're like, oh crap, I'm trying to make an inference about the population from my sample.
So then if we could do, also, if it's, like before, it said like, if the,
The 8% and the 12.5%. Oh, we're back on the Hobbit ones.
no, on like the actual notes, it said like, if the sample was good, then the proportion of the population is proportion of the sample. So we can infer that the population of the proportion of the population, we can use it for the sample standard deviation.
Which is why we're doing this whole confidence thing to justify to ourselves, is this sample good? That hits
But-
the whole percentage of the end thing.
I don't know, but I'm saying like, because, we assume that our sample is good, then we assume that our population proportion can be used for the sample as well. Therefore, we can find a standard deviation for the sample and use it to find a mean.
The only flaw in your logic is that at the beginning of this problem, they told us to assume approximately normal. So what we're doing is taking the sample, proving it's approximately, and then trying to, the whole population might not even be approximately normal. Why would the whole population?
Why wouldn't it be? If it's just randomly pulled from the population, that wouldn't be normal.
The population doesn't have to be normal.
It says it is.
Well, it said it was, yeah.
It's like, I don't know, I'm just thinking, because I remember the notes, it said that if your sample is good or whatever, then the proportion of the sample is the proportion of the mean or whatever.
Yeah, of the samples, of the sampling distribution. So you took multiple samples.
Does
That was
matter?
the world.
Does that matter though?
Don't you think? Because if we take a sample right now, again, of just this classroom, is that representative of the whole school? Is that a sufficient sample? Isn't that why we were saying we had to do a couple different samples?
But if we're assuming that it's normal, and we're assuming, because and we're assuming that, I don't know the word, but we're assuming it's just optimized, so that we can use that proportion for this.
This is the point where we lose our minds.
No, this is the point where Louise goes to. That's all. We have a lot. Like it's still math. We're fine.
I mean, as long as he's right, I guess.
Louise is just mad at the fact again that we're not using this formula. We're using this formula. But again, if we knew stuff about the population, why would we, like the whole point for the sample is to make an inference about the population. If we know the standard deviation of the population, who cares about the standard deviation of the sample? So, but I understand what he's saying. My God, I wish I had him in my next life when I actually had my act together a little better. He's going to let me finish this problem, and then he's going to let me figure out my words to come back to him. Okay, so he's going to pretend like he's okay with this. He's going to let it go and be like Elsa for half a minute. Okay, if he was okay with this. If he was okay with this, we could keep going. But heck, even if he's not okay, so I'm doing this again so I can convert this to a z-score because I like z-scores and I like looking at the table and I see. But if you want to be like Hunter, Hunter's not even upsetting Louise to begin with because he's just saying normal CDF. He's setting lower of 70.7. He's setting an upper of a 1 with a bunch of zeros. His mean is still 70.7. I think I put 0.7 before. And then, but I guess, Hunter, did you change your standard deviation to this, or did you leave it as 0.9?
I changed it.
So then Louise still has this problem. Mean or of 70.7 or more. I think it is supposed to be just 70. I think I'm being crazy. The mean is 70. Duh. If I drew my picture, which I should always draw my picture, it always helps me. Mean was 70. And we're asking what are the odds of it being 70.7 or above. The picture always helps me.
It's asking right now if this.
The sample will have a mean of this. So is it the old mean or is it this mean?
It's again, it's still saying what are the odds that normal is at 70. What are the odds that we're at 70.7 or above? So you could do this, change it to a z-score, convert, and get your percentage, or you could be like Hunter and do it all in the calculator, as long as you explain what you typed in your calculator, because if you just put normal CDF and a bunch of numbers with commas, they're not going to give you all your points. And when you do that, you end up getting an answer. Yes, ma'am.
Tangeline left her purse down in your room. Are you going to be there a minute?
Yes, ma'am.
Thank you.
Okay, and what number did you get? Is it super small?
Yes.
0.00695?
Yes. Correct. Changed it back to 70.
Wait, hold up. Will you do the Z part?
If I did the Z part, I would do what you wanted of 70.7 minus 70, but instead of dividing by 0.9, I'm going to divide by 0.02846. It's 0.00, so it's really small, 0.7%, he's right. Okay, so if the filling equipment is functioning properly, what is the probability that you will have a mean of this? We figured it out, and it was that. Based on our answer, would you suspect that the loading mechanism was overfilling the cars? Yeah, so mean sample size of only 10, only about 7.7% of the time the machine must be overfilling. So I'm pretty happy with that. So what do we expect? Are we happy? We just said overfilling the cars. I would say no, but maybe you want to argue yes because you're still mad at life. No, because with a sample size I know why. Okay. With a sample size of 10, only 0.7% of the time do we expect the machine to overfill. Okay. I'm going to start recording and say more words. It's cool with me if you're packing. So you know how in calculus